Welcome to this explainer. Today, we're unpacking the ultimate heavy engineering balancing act, scaling up wind energy. We're going to dive deep into materials efficiency, taking a technical look at how manufacturers optimize the use of raw materials, things like steel, to cost-effectively scale up turbine size, rotor sweep area, and overall energy output, all without bankrupting the project.
So, how exactly do we build bigger turbines without breaking the bank? Well, to produce energy at a lower cost, wind turbines literally have to grow in size, but that presents a massive financial and engineering challenge. Obviously, we want to harness more wind, which means building taller towers and much longer blades. But here's the catch. Those massive structures require an absolutely incredible amount of physical material. It's a true heavy engineering puzzle.
We call this the growth paradox. On one hand, taller towers and wider rotors mean more energy. But on the other hand, they require vastly more raw materials, and those materials are highly susceptible to price volatility. In recent years, the industry has realized that just building bigger simply isn't enough anymore. You have to build smarter. Think about it. If the cost of the steel or carbon fiber outpaces the value of the extra energy generated, well, the whole financial model just collapses.
Here's our roadmap for today using the SASB framework. We'll be covering the wind turbine growth paradox, why materials efficiency matters, tracking top materials consumed, measuring top head mass, designing for optimization, and finally, we'll look at the future of wind energy.
All right, let's jump right into Section 1, the wind turbine growth paradox.
To really wrap our heads around this paradox, we have to look at the core tension driving the industry right now. The ultimate goal is cost-effective energy, right? But massive material inputs, like steel, are a huge cost driver, and they have a notorious history of severe price volatility. The long-term success of the wind technology and project developers industry hinges entirely on one thing: its ability to offer energy at a comparatively lower cost than fossil fuels or other renewables. So, if steel prices spike and manufacturers haven't optimized their designs to do more with less, that price volatility directly threatens their market competitiveness.
Moving on to Section 2, why materials efficiency matters. So you might be wondering, how do we actually track if manufacturers are successfully navigating this paradox? Well, they rely on the SASB standards. It's an authoritative framework now managed by the IFRS Foundation, and it's used to measure exactly how efficiently these massive structures are built and scaled. These standards basically give us a shared language, really specific metrics that allow us to objectively evaluate how well a manufacturer is handling materials efficiency and managing their operational risks.
Which brings us to Section 3, tracking top materials consumed.
Let's take a look at our first metric, SAS code RRW 440B.1. Under this, manufacturers have to report the top 5 materials consumed by weight in the final delivered turbine. We're talking specifically about the nacelle, blades, and tower, and this strictly excludes waste or installation freight. If you notice the breakdown here, the tower relies heavily on iron, steel, and aluminum. Meanwhile, the nacelle and blades consume high volumes of carbon fiber, fiberglass, and copper. By isolating just the final delivered weight and completely excluding construction waste, we get a pure, unadulterated look at what it physically takes to put that turbine in the sky.
Now, this precise breakdown is categorized by specific wind turbine classes. And that's because, as you can probably guess, an offshore turbine faces wildly different structural demands than an onshore one. The International Electrotechnical Commission, or IEC, defines these classes based on things like rating, turbulence characteristics, and whether the turbine is sitting in a grassy field or out in the middle of the ocean. This distinction is absolutely vital. Optimizing a massive Class 1 offshore turbine requires a completely different engineering approach than a Class 4 onshore turbine.
Next up, Section 4, measuring top head mass. If you want to see the ultimate scorecard for heavy engineering efficiency, you have to look at top head mass. This basically accounts for all the heavy machinery sitting at the very top of the tower, minus the blades themselves. You've got the nacelle, which houses the generator, the gearbox, and the control electronics, and then the rotor that connects to the blades. By strictly excluding the blades from this metric, engineers can neatly isolate the efficiency of the mechanical and electrical core of the turbine from its aerodynamic components. It's a really clever way to measure it.
So when you divide this top head mass by the turbine's capacity, you get T/MW, metric tons per megawatt. This is a single, critical ratio that reveals exactly how much physical weight is required to generate just 1 megawatt of nameplate capacity. And let me tell you, this is an incredibly powerful number. If a manufacturer can lower their metric tons per megawatt, it means they're successfully scaling up the energy output of the turbine without proportionately ballooning the massive weight sitting hundreds of feet up in the air. For sure, that translates directly to lower material costs and a way more competitive product.
That takes us to Section 5, Designing for Optimization.
Knowing the weight is one thing, but how do manufacturers actually engineer better efficiency? Under metric RWT-440B.3, they disclose their optimization through 3 core steps. First, reducing raw consumption. Second, squeezing more capacity out of the materials they do use. And third, extending the turbine's total lifespan. This isn't just about making things lighter, you know? It's a completely holistic approach. It's all about careful material selection, prioritizing innovation, and setting really strict objectives around how those materials are going to perform over decades of relentless wind.
Now, here's where it gets really fascinating. Efficiency isn't just about physical hardware. It actually includes software innovations that maximize output. Systems like SCADA, which stands for Supervisory Control and Data Acquisition, essentially act as the brain of the turbine. By intelligently pitching the blades and controlling the rotor speeds based on real-time wind data, this software can dramatically increase the turbine's capacity factor. So this allows manufacturers to generate more electricity from the exact same physical structure. It radically improves the materials efficiency equation without adding a single ounce of steel. How cool is that?
Back in the physical world, design modifications span everything from lowering tower weights high up in the sky all the way down to cutting material waste during foundation installation in the ground. Think about it like a cascading effect. When engineers design a lighter top head mass, it means a lighter nacelle. A lighter nacelle means you can build a lighter tower, which in turn means you need way less concrete and steel for the foundation. Literally, every kilogram saved at the very top saves exponential material and cost all the way down to the dirt.
Finally, let's look at Section 6, the future of wind energy.
So the big takeaway here is that achieving massive scale in wind energy is entirely dependent on this obsessive focus on materials efficiency. Which leaves us with a pretty fascinating final question. As the world demands even larger turbines, what breakthrough materials will engineers pioneer to power the next generation of clean energy? Are we going to see new carbon fiber weaves, advanced alloys, or even smarter software? Whatever it is, what we know for sure is that tracking these SASB metrics will be the absolute key to watching that future unfold. Thanks so much for joining me on this explainer, and keep your eyes on the skies.